Okay, for our final book lesson of the week, we are once again in 812. You printed those note sheets off yesterday, and I said we would finish it up today in this lesson. So make sure that you do have the second page of the 812 notes. We left off at 830. We did that. So now we are on 831, and we're going to finish from there, okay? So let's go ahead and read kind of this new way of looking at polynomial functions. So 831 says, you can use a number line to represent the x values for which the polynomial graph is above or below the x-axis. The bold part of each number line shows where the output values of the function are positive. Okay, so bold means positive. That is where the graph is above the x-axis, because outputs deal with y values. So if they're positive y values, they are going to be above the x-axis. Okay, now on the other hand, we need to know that the open circles are representative of the x-intercepts, or we can call those the roots of the function. Okay, and then thirdly, where there is no shading, the value, the output, the y value of the function is negative. Sketch a possible graph to fit each number line, then write a possible equation. So this is two things. We're going to sketch the graph, we're going to write the equation, and we need to keep in mind that each number line represents the x-axis for a different polynomial. Okay, so what we are going to think about is not the height of the peaks and valleys, but basically where is the graph changing direction, where are the peaks and the valleys, and where are those x-intercepts. Okay, so let's on number one start off and see that the positive values are in the bolded region. So maybe to help yourself out, also if you're taking notes on a blank sheet of paper, you definitely want to draw these number lines to begin with so you know what we're working off of. So in these regions, we're going to have the graph above the x-axis, and then in these regions we're going to have the graph below. So when I go ahead and draw my xy coordinate grid, okay, I first want to probably place my -3, my -1, and my 4, because those are given as the x-intercepts because they are open circles. And then I see that I am going to start below the graph, but then I need to go up in the positive region between -3 and 1. Okay, so I'm going to go up toward -3, but then at -1, I'm going to then dip below all the way till I'm at 4, which is another x-intercept, and then bold means it needs to be above. Okay, so we can see that in this region we are above the x-axis from -3 to -1, and from 4 to beyond we are in the positive region as well. Everything else is below. All right, so if we're color coding, maybe we represent negative with green. Actually, let's do negative with red because that's a common color that we associate negative with. Okay, so then the negative regions are going to be below the x-axis. So what is a possible equation for this? Okay, well, we need to think if our x-intercept is -3, what is the factor going to be with it? It's going to be the opposite. So we're working backwards, x plus 3. Okay, what would be the factor associated with the x-intercept of -1? It would be x plus 1. And then finally, we would have x minus 4, because that's the opposite of positive 4. Now we notice that what we just wrote has a degree of 3 factors, makes a degree of 3, so we know that the end behavior is going to have to be opposite, and we can check and see that it sure is, and it's behaving like a normal cubic graph, so we don't have to put a negative out front. So I'm just going to put y equals, and this is a possible equation. Now, it's not the only equation that could pair with the number line, but for now, we are satisfied with it. Go ahead and put me on pause if you want to try a few of these on your own and then check your answers. If not, hang with me. Okay, so now we see that we are given positive needs to be between -5 to 2, but something needs to happen at 0 because that is given as an intercept. Okay, and then what is our negative region? It has to be from negative infinity to negative 5 and from 2 to positive infinity. So I'm going to go ahead and make my axes. Okay, and I'm going to first draw in my intercepts, negative 5, 0, and 2. Okay, and I see that my graph starts negative. But then we are going to go positive, but then it has to come back to the x-axis at 0, but then it has to stay positive until we get to 2. Okay, so I'm going to kind of backtrack and do that again because I'm thinking in terms of kind of making the peak and the valley look nice. So we have to dip down, come up, but then dip down again by the time we get to 2. Okay, so let's look back at our number line. We said from negative infinity to negative 5 is going to be negative. And then we said from negative 5 all the way to 2, we have to stay above, but we had to bounce at x equaling 0, okay, which happens to be the origin. And so then from there, from 2 to infinity, we are negative. Okay, so that is going to be our graph. So if we make our equation, okay, we can see that if we just do what we did on the last problem by writing out our factors, which that's what we're going to start with. So we have x plus 5. We have to do the opposite of what we see. We have x, I'm going to write plus 0. And then we have x minus 2. What degree is that? If we just leave that alone, that is the third degree. But if we notice the end behavior is the same, so because the end behavior is the same, we know it has to be an even degree polynomial. Okay, now we have to pay special attention to this x-intercept of 0 because what is happening at that x-intercept of 0? It is kissing the x-axis. So what did we learn about things that bounce or that kiss? They have to have an even degree on the factor. So I have to go in and I have to add this degree of 2 on the x plus 0. Okay, so you definitely want to highlight that. Okay, because that's up to you to come up with. So when I add that, we now get a degree of 4, which is an even degree, but we also have to think about, usually when we think even degree end behavior, it's an upward parabola. But in this case, we have both end behaviors going down in the downward direction, so that means the orientation has been flipped, so we have to put a negative out front here. So we have y equals... Okay, now I'm going to say that the order of things is probably going to be switched because if we look at this x plus 0, what is x plus 0? It's just x. So I'm going to do a little erasing and write it the way that we would normally see this written. Okay, we would have y equals x plus 0, but I'm not going to write plus 0. That had to be squared because it was kissing the x-axis, times, and then we'll put x plus 5 times x minus 2. So maybe I want to scoot that over. Okay, let's highlight again. Draw in our arrow, and we said x minus 2. Okay, so there is our equation. But what did I forget? I forgot my negative. Man, I'm sloppy today. Okay, so y equals negative x squared. The negative has to be there because of the opposite end behavior or the opposite orientation of the end behavior. Quantity x plus 5 times quantity x minus 2. All right, moving right along to our next problem. Okay, we see that we are negative from negative 1 to 4, and we are positive from negative infinity to negative 1 and from 4 to infinity. Okay, so again, you can always write positive, but we have to be careful of that x-intercept in that negative region. Okay, so I have my x-intercept of negative 1, I have my x-intercept of 1, and my x-intercept of 4. And then from here, I am going to think about starting in the positive region and then dipping down into the negative region at negative 1. but then when I get to positive 1, I have to kiss because I have to stay in the negative region. But then by the time I get to 4, I need to be entering back into the positive region. So we see that our end behavior is the same. So what does that mean that our degree has to be? It has to be even. So if we simply use our 3 x-intercepts, we're not going to get the correct equation. Okay, but we can start by doing that. So we can write out x plus 1. We can write out x minus 1 and x plus 4, minus 4. And then we can think about what is going to be the factor, okay, that we are going to be considering in this case to be the, I'm looking for the word we used yesterday, the double root. Which one is the double root? Well, it's the one that's kissing the x-axis. So in this case, the x-intercept of positive 1 is where we are going to make it the double root. So we have to look at the factor that's the opposite because that would produce positive 1. So we have to put a square and make sure to highlight that on x minus 1. Now, because the end behavior is up, up, that's just what we would expect on a normal upward parabola. So do we need a negative? We do not. So here is the equation. Y equals quantity x plus 1 times the quantity x minus 1 squared times the quantity x minus 4. Okay? Finally, we have one more, and we see that our positive region is -2 to 1, -1, 1 to 2, and then our negative region is everything on the outskirts. So, if we go ahead and make our axes with our x-intercepts, okay, we have -2, we have -1, 1, and 2. And we start in the negative region, okay, and then at -2 we go to the positive region, and then at -1 we go to the negative region, at positive 1 we go to the positive region, at 2 we then dip to the negative region. So we see that our end behavior is the same, so it's going to be an even power, which makes sense because we have even amount of numbers, 4 numbers, but the end behavior is the opposite of what we usually see. So this is called negative end behavior. I'm going to try to use our vocab a little bit more than maybe I have been. This is called negative orientation. Okay, so at this point we can go ahead and think about our equation. Y equals, we see that negative right away because we're both pointing downward. And then we have x plus 2 as our first factor, x plus 1. Then we have x minus 1. And then, I don't know if I can squeeze that in, so I'll put it right here, x minus 2. That is our equation, and we see that it is a degree of 4. 4th degree, but the orientation is negative. Okay, so if we look back at all 4 of these examples, okay, which ones have positive orientation? Okay, well, this is on A. We see that this is positive orientation. On letter B, we see that this is negative orientation. We see on C that that is positive orientation because it's like a normal parabola. And then on D, we see that that is, once again, negative orientation. Trying to use our vocab there. All right. So, it says, what can we say about graphs of polynomial functions with even degrees compared to graphs of polynomial functions with odd degrees? Use what we did in 8.1.1 and maybe what we just did to justify our response. Okay, well, if we are looking at end behavior, that's really what I want to focus on. So for end behavior, we see that if we have even degree, we know that the end behavior is going to point in the same direction. You feel like we've written this millions of times? Because we have. And then if it's an odd degree, our end behavior is going to point in opposite direction. That is what I want you to have mastered. Okay, now if there's a negative, then we're going to call it having negative behavior, and that is going to be kind of the opposite of what our parent functions tell us. All right, so now it says choose 3. I'm going to do all of them. I would suggest you do all of them for practice as well. But what we want to do is create a number line for the graphs, but we want to look back at our 811 note sheet, which I have pulled up for my video. So if you go and pause me, grab your 811 day 2 note sheet here, okay, we don't have to do these from scratch. So they want you to look at the pictures. So if we look at polynomial 1 from the 811 note sheet, we're looking at the graph, okay, we see that what are the x-intercepts? The x-intercepts are 2 and -5. And then from there, we can think about the number line. So we have to draw in our number line first. Okay, and we have, I'm always going to put maybe my 0, or no, I don't even have to do that. I'm going to put in my -5, and then my 2. Okay, our open circle should be on our x-intercepts. And then if we look at the graph, we see from -infinity all the way to, all the way to 2, it is below the x-axis, so we're negative. But then when we get to 2, it pops above. So what are we going to, sorry about that, what are we going to shade? We are going to highlight, I'm going to use my highlighter. We are going to go from 2 and beyond. And that's all we shade, okay? Because everything here is below the y-axis, or the x-axis, meaning negative values, and everything here is above. So the number line with the shading is what I would expect to see for problem number 1. Okay, now for polynomial 2, if we look at that, okay, we don't even have to look back at the picture when we're given these equations to draw the number line. Okay, we have +2, -2, and +3. So -2, +2, and +3, because it's the opposite of what we see in the factors. And these need to be open circles because they are x-intercepts. Okay, now we need to look back at the picture that we were provided. So P2, we see that we were below until we got to our first x-intercept. Then we were above until we got to the second, then below, then above. So kind of the normal trend that we would expect. So negative, positive, negative, positive. So if we stick with that, we're going to shade the positive and the positive. And I probably don't want to get sloppy. I want to draw in my arrows. So there is our second number line. Okay, on the third polynomial, it is not factored, so we cannot just look at it and know what the x-intercepts are. So if I go ahead and I look at the graph, what were the x-intercepts on P3? Well, it looks like the x-intercepts were about at -5. Let's see here. They were at, let's zoom in, about -5, 0, we'll say maybe 1, and 4. So we have -5, 0, 1, and 4. And then we're going to think about our shading. So at first on polynomial 3, we were above, then we were below, then we were above for a little time period, then below, then above. So we start above and we just switch back and forth. So we have above, below, above for a little period, below, and then we end to infinity. And here you can see that when we have two shaded regions on the end, that represents kind of the same behavior. So that would be an even degree, which it is an even degree of 4. But then when we look back and we see that one end is not shaded and the other end is shaded, that would be an odd degree, okay, which it is. It's 3. So this would be even, that would be odd. Okay, some good things to start seeing. Now we see that this next one is going to be odd. It's going to be degree 5 right away when we look at that. So if we take advantage of the factored form and draw in our number line, we can, okay, put in our -3, our -1, our +1, and our +5. We can make those open circles. Shame on me for, on the last one, not putting in my circles. Okay, and then if we look at the graph, we can probably guess what it's going to be if it's odd and there's no negative out front. We know that it's going to be shooting in the downward direction, so I'm guessing P4 is going to start below the x-axis, but let's check and see. So P4 is, yep, it starts below the x-axis, but then it kisses at the first x-intercept of -3, and then it comes back and crosses our x-axis at our next intercept, and then from there we're gonna alternate. Okay, so because we have the squared here, we know that we're going to stay below the x-axis for the first 2 intervals. So we have our negative region, so we have a negative here and a negative here, and not till we get to -1 is it going to pop above, and then because the powers on all other factors are simply 1, we're then going to alternate. So we would have above, below, and then it would shoot to infinity. Okay, so again, we could predict kind of what was going to happen. We see that the end behaviors are different. There's no negative, so we're thinking of our cubic parent function, and there is our number line. Again, hopefully you're trying some of these on your own. Okay, so now on P5, if we look, what are our factors going to be? Well, this is in factored form, but I am going to see that I have 0 is going to be 1, because if I set -0.1x equal to 0, I'm going to get x equals 0, so I'm going to put an open circle at 0, and then -4 is going to be my other intercept, and so I'm going to put a circle there, and I can think because it's negative and it's going to be degree 4, I know that I'm going to picture 2 downward arrows as its end behavior. So I'm guessing that in order to do that, okay, we definitely can't have highlighting at both ends of the number line, so we have to leave both of those open. But in the middle there, we've got to see what's going on. So if we look at P5, P5 is going to go ahead and go above between the 2 intercepts that we have listed, but it's going to be below on both ends for that end behavior. So we can go ahead and highlight in between here and be satisfied with that number line. Okay, on this next one, P6, it is not factored, so we are going to go ahead and rely on the graph for this number line, but instead of diving in, I'm going to say let's go ahead and skip that one and being nice today, and let's move on to the final factored form on P7. So on P7, I can see that I have 4 factors that all are the first power, so I have a degree 4. I don't see a negative, so I know that the end behavior is going to go up and up. So my factors are -1, 0 because of that 0.2x, positive 3 and negative 4. Bummer, I didn't do that correctly. So let's go back. Let's call this negative 4, this negative 1, 0, and 3. So all of these are our open circles, and we said that because it's degree 4 and there's no negative, we know that on both ends it's going to shoot up in the positive direction, okay? But then in between, we can guess that it's going to most likely change from positive to negative to positive to negative. But let's go ahead and look at our graph. So we're looking at graph 7, so I need to scroll down a little bit. But we can see it's positive, and then at the first intercept it goes negative. Then the next one it goes positive for a bit, then negative, then positive. So because there are no additional exponents on the factors, we can just switch back and forth. So we have positive, negative, positive, negative, positive. All right, and again, I'm feeling nice, so we are going to go ahead and say x on polynomial 8. So the final activity that we are going to do in 8.1.2, and I encourage you to pause me and try this on your own as well. This is a great opportunity to check for understanding, is without a calculator, let's make a rough sketch of the following functions. Okay, so we need to analyze everything we've talked about up to this point. So the first thing that I'm going to notice is the degree. What is the degree of this one? It's degree 3. Okay, but we can't overlook the negative out front. So when I see degree 3, the end behavior is odd, so it's going to be opposite, but we know that it is going to be negative orientation. Negative orientation. So what does that mean? Okay, it's the opposite of a cubic graph. So the first part is going to go up and the last part is going to go down. So now I have to look at my x-intercepts. My x-intercepts are going to be, let's see, negative x equals 0. So that means x has to equal 0. X is going to equal negative 1. X is going to equal 3. So now when I sketch my axes, I'm going to put my negative 1, my 0, and my 3. And then I'm going to think about my end behavior and the fact that none of the factors are being raised to powers. So I'm going to start up because I know my arrow is pointing up. And I'm going to go down, up, down. And there is my graph. You can see that it has opposite end behavior of our parent cubic function. It is odd degree, so it's opposite, and there would be our sketch. All right, so on this next one, we have a degree of, let's see, 4. Don't overlook that exponent. So the end behavior is even, so it's going to be the same. And I don't see a negative, so we know it's going to be like a normal parabola that shoots up and up. So in this case, though, we only have 3 x-intercepts. That is going to be at 1, negative 2, and 4. And I'm going to highlight the 1 because at 1, it's an even exponent, so it is going to bounce or kiss off of the x-axis. So I'm going to go ahead and make my axes. And I'm going to write in my x-intercept. So I have negative 2, I have 1, and 4. And I need to start shooting upward because it's the normal even-powered end behavior. And I'm going to go down, but then when I get to 1, I'm going to bounce, and then I'm going to shoot up because I have to change direction at the bottom of that peak so that I can get my same end behavior. Okay, and on this final one, I see that I have a degree of, what is it? It's 4. So that means that the end behavior is going to be the same. And again, I don't see any negatives, so it's going to be like a normal parabola. I'm going to go ahead and draw in my intercepts. So what are my x-intercepts in this case? It's going to be negative 2. And we are going to say that negative 2 is a triple root because it is repeated 3 times. And then we have a positive 4. And I'm going to start with my upward end behavior at the back of the graph. And when I have a triple root, what's it going to do? It's going to level off but continue in the same direction. But then from there, I have to return back to my x-intercept, which is just taken to the first power. So I'm going to continue to cut through the x-axis. So this is kind of a unique graph. You might make yourself a note at this point that we are going to simply level off due to the odd exponent. Okay, that's maybe something that's probably not as mastered by us because we haven't seen it as many times, but it is unique in that it's not making that normal W shape even though we are at the fourth degree. Okay, so there are the 8.1.2 notes. This is the last big note sheet of the week, so great job. Make sure to finish up that 812 homework and let me know if you have questions.